much for joining us for tonight's Café Scientifique, the Nottingham Contemporary issue. I know that these have happened elsewhere before, so it's very exciting for us to be hosting this evening. I'd also like to extend a thank you to Raphael Hefti, in his absence, because via his work we've been able to explore very exciting things such as molecular structures in chemistry and chemical processes and reactions, which I, for one, haven't turned my attention to since I failed chemistry in the Leaving Cert in Dublin several years ago. So it's been quite enjoyable to revisit or look into an area that rarely crosses paths with the visual arts. So just to tell you a little bit more about the exhibition upstairs, I hope that most of you have had a chance to take a look at the work. But Raphael is an artist who's driven by intense curiosity and a certain fearlessness, experimenting with materials such as aluminium, copper, zinc, glass, and the slightly poisonous lycopodium, pushing them to perform in ways that might frustrate a scientist, yet delights Hefti as an artist. Seeking out the mistakes in industrial and chemical processes allows Hefti to produce objects of strange, alluring colours that might be deemed wrong or faulty products. And so based on this reading of the exhibition, I'd like to extend a very warm welcome to Professor Martyn Poliakoff, who's research professor of chemistry at the University of Nottingham and a pioneer in the field of green chemistry. And Martyn has generously offered to shed some light on the nature of reactions, and in this case the accidental reaction, which is embraced by Raphael Hefti. And so just to say thank you all very much for coming. There will be a presentation from Martyn, and then we'll have a little break if you want to get another drink or anything, and then we'll have questions from the audience. We are recording this evening's talk, and Chloe, our gallery assistant, has a microphone, so if you would like to ask a question, just make yourself known and I shall point you out and get a microphone to you so that we can capture your comments on the recording. And so I will hand over to Martyn. Thank you.
Thank you. So I'm Martyn. Chloe, you can come closer. You don't have to sit. So you can sit in a comfortable seat. The more expensive seats. So I'm Martyn, and as you can see, I look like a professor. And I work at the University of Nottingham, and I'm a chemist. So I've only just looked at the exhibition very briefly, so you cannot, you're not going to get profound reflections on the various exhibits, though I do like the tubes, particularly the titanium tubes that are brightly coloured. But what I thought I would do is that I wanted to talk to you about what I perceive as the differences between... Is it still working?
The batteries might have gone.
Just the microphone.
Carry on.
I wanted to show you what I perceive as sort of the differences between the way that an artist works, or I think an artist works, because I'm not an artist, and the way that scientists work. So I thought the way I would do it is that I have brought a bag of objects from my office, which I will now show to you. So I leave them in the bag, so it's a surprise. So the first object is a bottle of water. It's real water. I will just demonstrate. It's quite safe. Well, you know, it's reasonably safe, though I could keel over later. But now, because I'm a chemist, people sometimes bring something like a bottle of water and say, can you analyze this? And the answer is that that's a completely impossible question for a scientist to answer, because the question is, what do you actually want to know about the water? Now, you can analyze it in the way that I've just demonstrated. I can drink it, and if I'm okay, well, we know there's nothing really poisonous because I haven't yet keeled over. And if you waited longer and longer and longer, you could tell, all being well, that there was nothing poisonous at all. And if you waited a week, you could tell that there wasn't some organism in it that was going to give me stomachache or whatever. But the sort of question which people do ask me is, if you have a plastic bottle with water in it, does stuff from the plastic dissolve in the water? And that's a much easier question to answer, because you can start thinking of doing experiments. And the first experiment is that you can tell that not very much will be leaching into the water, because if you look at the bottle, this one doesn't have one, but they usually have a sell-by date, which are usually something like a year after you first buy it. So if something was going to dissolve out of it, it would dissolve, it must be dissolving quite slowly. And there are ways of analysing water so that you can measure small amounts of carbon compounds. The plastic is a carbon compound, so you can analyse it, and you could probably show that there's very little in it. Then, if you thought, you might think, well, very often things dissolve better in hot water than in cold water. So you could try emptying out the water, like I did this morning, and try putting hot water into the bottle. And so here's a bottle in which I have put hot water. And you can see it's really gone quite funny. And if you put one next to the other and use the menu, I should say there's very nice food here, but not now. If you put the menu, you can see that there is actually a space. So the bottle has shrunk. And so this tells you nothing really about what dissolves, whether something dissolves or not, but it actually tells you quite a lot about how a bottle is made. And if you're not familiar with this, a bottle like this is made from something like this, which is called a preform. And the preform has a neck at the top, which is exactly the same size as the bottle. You can screw the top on it. And then this goes into a mould, and the bottom part is heated up, and compressed air is blown in, and it's blown into whatever shape you want for your particular bottle. And because plastic is a sort of material that has at least a partial memory, if you heat it up, it shrinks back again. And I'm not sure, well, the bottle got so hot with boiling water in it that I dropped it, so that's why it sort of stopped at this size. I don't think you could shrink it back to that size, but accidentally, by thinking about what dissolved, you can see you get back to thinking how the bottle is made. So that brings me to the second object in my bag, or the second sort of object. This is a dog toy, and it squeaks. And surprisingly, there are dog toys. You can get a whole series of different dog toys that are shaped rather like molecules. And I use them for my teaching, because you see, even the guys at the back can sort of see the shape over there. And also, if the students are getting a bit bored in the lecture, if you squeak it, hi, come in, Alice. It's a nice seat here. If you squeak it, it cheers the students up. And so the reason I wanted to show you this is because this is actually the shape of one of the molecules that I studied in my PhD, doing my doctorate.
Pardon me, excuse me, sir. Does everybody in the room know what a molecule is? Could you explain?
A molecule is a collection of atoms. And each chemical compound has, it's a generalization, has a different arrangement of atoms. Do you know what a molecule is? Or is that why you were asking?
Well, yes, but I was hoping you might explain.
That's quite... Look, let's perhaps... How many people here have studied chemistry more successfully than Emma? So... Well, you have, yes. So 4 or 5. So don't worry, because you don't need to know any chemistry at all. But atoms in a chemical, everything in the world is made out of chemicals. And so the Royal Society of Chemistry, which is the professional organisation of chemists, has
Are ideas made of chemicals?
Yes. Well, in your mind, it is chemistry. I'm sorry, the question was, are ideas made out of chemicals? And I think the answer is, the idea itself, which is a thought, is not made out of chemicals, but how it is stored in your brain, or how it is written down in a book, or is based on chemicals. How the way it is stored in a computer is in terms of electrical charge, but the computer itself that stores that charge is made of chemicals.
But the idea?
The idea, well, let us leave that for the discussion. We have a whole hour or more for discussion. So the molecules consist of atoms joined together, and in my doctorate, I was looking at a molecule that had an iron atom in the middle and other groups round about. And at one point, quite early on, I asked the question, or my supervisor asked the question, what would happen if you removed one of these atoms? What would happen to the rest? And the idea was, and you're very privileged, this is my most expensive dog toy. It's a precision German dog toy. And it's good because it waggles. And the idea was that, we thought, was that if you have only 4, they would arrange themselves in this shape, which is probably familiar to you, but you may not know is called a tetrahedron, where you have the 4 atoms arranged symmetrically around the one in the middle. So there I was, I set up an experiment, the details of the experiment don't matter, where I expected to observe a tetrahedron. And I didn't. Because it turns out that the molecules are cleverer than we are and understand things better, and it had rather a strange shape which was distorted, something like this. And I had a colleague, Jeremy, who worked in the office next door, who understood theory, and he developed a new theory which explained how these atoms behave. And in fact, we both won a medal from the Royal Society of Chemistry for this. So, but the thing is, and the difference, I believe, from the artist, Raphael, is that we had a hypothesis. We thought, when we do this, we should get that. Now, of course, when we got something else, we had to change our idea, but we didn't just say, for the hell of it, let's see what happens if we do so and so. So, we have the next object. So, this object here is a piece of a chemical reactor. A reactor is something in which you do a reaction made out of metal that was made by my students. So the idea was, in a bit that's no longer here, a mixture of chemicals and water were passed through this tube, which was heated up. So this is a heater. And then it passed through this tube and then out at the bottom. And the heater, which is this grey thing here, is surrounding an aluminium block. So you've got it. There's a heater here with a tube down the middle. And so my students were quite proud. And these two things are the electrical wires that take the electricity in to heat up the heater. And of course, when you heat something up, you need to control how hot it is. And so sticking in here, there was also a temperature measuring device, the so-called thermocouple. Unfortunately, when it was switched on, or before it was switched on, the student using this forgot to put in the temperature controlling thermocouple. So it just got hotter and hotter and hotter, and it eventually went above 660 degrees centigrade, which is the melting point of aluminium, and the aluminium block melted. And so if I turn it round, you can see the aluminium ran all the way down, red hot, and then cooled down and stuck. So I have this in my office because I think it really looks fun. It has absolutely no scientific merit, except for the fact to be a warning to students to be careful and to make sure they put the thermocouple in and so they can control the temperature. But this is an example where at least the student was trying to do something serious, and we got quite a fun result. And I don't know how many of you have seen photographs of Chernobyl, the nuclear reactor that melted. There is a very similar, but much larger scale, solidified melted nuclear fuel, which is known colloquially as the elephant's foot, and this reminds me very much of the Chernobyl reactor. So I have this on the table in my office just to amuse visitors. But again, it shows that even when you're trying to do something quite scientific or quite engineering, you can get quite nice objects. And the final object, well, actually I've got one more, is this, which looks like some sort of exotic mineral. This normally hangs on the wall in my office, so I took it down especially for you. And actually this is a piece of plastic. And it's a piece of plastic that I found on a beach of one of the lakes in the Lake District. And what appeared to be, I mean, if you looked at the thing, was that somebody had had a bonfire and thrown a large lump of plastic onto it, and this had melted to make something that looked really quite artistic. So what I think is interesting is that nobody could make something like this deliberately. They could try throwing lumps of plastic onto a fire and pick out the lumps that look interesting, but there's just too much randomness in a fire, the way you throw things onto it and so on, that you could actually produce something that looked exactly like that without a huge amount of work. And you could never get the colouring like that because there may have been a mixture of plastic, so there was a whiter bit there than there and so on. But on the other hand, even boring chemists like me can look and say, well, that looks quite nice, and pick it up and then hang it up in my office. But making that by burning plastic is not really doing anything scientific in the sense of the way that chemists do science. And then the final thing that I wanted to show you before we before we break, is a periodic table. The periodic table, if you don't know, is a way of writing down the symbols of all the known chemical elements, which was originally devised by the Russian chemist Mendeleev in 1869. In Russian, it is called the Mendeleev's table. And I just got a letter 2 days ago from the Russian Academy of Sciences. They want people in the West to start calling it Mendeleev's table as well. And they want my help in persuading people they should do. I don't think anybody's going to change the name. But the periodic table is for chemists very much like a map. It helps them understand how different elements react and behave. In fact, that's why Mendeleev devised it. He was writing a textbook for his students, And he thought there was this huge mass of facts, and if he laid it out like this, it would make it simpler. And he made a whole series of predictions by looking at his map, saying there should be an element there should be an element there, and so on, which were then discovered. So he became really famous.
Sorry, would you explain what an element is?
An element is that's a very nice question. You see, if I was doing GCSE, I could run off the definition of an element straight away. I think chemically, well, before the end of the 18th century, nobody believed in atoms, although the idea of atoms had been developed by the Greeks. The Greeks thought if you take a piece of something and you cut it in half and then you cut it in half again, you will eventually get to a stage where you can't cut, even if you had a really tiny knife, you couldn't go on cutting it forever. So there must be some ultimately small bit of matter, which is an atom. And during the end of the 18th century, it was realized that there were different sorts of atoms, hydrogen, oxygen, and so on, and that these combine together to make different compounds. So hydrogen and oxygen can form water, can also form a molecule called hydrogen peroxide. And once this idea of elements had got out, that had been formulated, people started finding elements everywhere. And it was a big business. People isolated new element and started selling it at quite big profit. And in London, it was a big industry, people discovering new elements. And now we know that there are 118 elements that are likely to exist. It's possible that there's slightly more, but there are only 118, and of those, some of them decay into another element so quickly that you can largely discount them. But in Mendeleev's time, in 1869, he predicted the existence of some elements which had not previously been isolated. And over quite a short period of time, people discovered elements. They were extremely patriotic in those days, so they tended to name them after their own country. So the French called it their element gallium, after Gaul, and the Swedes called it scandium, after Sweden, and the Germans, not to be outdone, called it germanium, and so on. And so Mendeleev became really famous because he predicted the existence of 7 elements that were then discovered to exist. The 7th one was discovered after he died, so he was already famous by then. What is usually forgotten is that he was less successful and predicted some that didn't exist, but that's now forgotten because people remember his success rather than his failure. And of course, as a chemist, I have been used the periodic table ever since I was at school. Though interestingly, my first chemistry book at school didn't have a periodic table in it. But in the last few years, since 2008, I have become very much more involved in the periodic table because a video journalist in Nottingham suggested to me and my colleagues that we should make one YouTube video about every single element. And in a mad 5 weeks, we made all these videos, 118 videos. Well, in fact, 120 because there was an introduction and a trailer. And these have become really very popular to the extent that when I travel around, I'm accosted by people in the most unlikely places who are fans of our videos. Last Monday night, I was emerging from Piccadilly Circus Station at about 10:30 at night, and the top of the stairs was a young woman who said, "Hello, Professor, I'm a fan of your videos." And she was a Polish chemistry student visiting London. Anyway, what I wanted to do, just to finish up this idea of accidents and accidental chemistry, is to show you a short video. Then we will stop for getting a drink, and then you can ask me lots of questions. Not only you, but other people as well. But you've asked some really good questions. Thank you. So let me now show you this video, which I think is quite funny, particularly because it makes me look incompetent. I'm now going to do one of my favorite reactions. It's not very spectacular, but I think it's very satisfying. It's the reaction between hydrogen peroxide and potassium permanganate. Let's begin with a bit of water. So I'll add some potassium permanganate, which gives it a nice pinkish purple colour. You've probably heard me saying already that my grandfather used to put permanganate in his goldfish tank so the fish would swim round in purple water. Didn't seem to do them any harm. We now add a little bit of sulfuric acid. The acid doesn't change the colour at all. So you can see now we've got some nice purple potassium permanganate, and now we will take some hydrogen peroxide. Sam had a big bottle that she needs to be used up, and we'll add it and see if we can see anything happening. So watch carefully. I think it may be flat. I'll try another bottle. I'll get some of my own hydrogen peroxide instead. Flat? Yes. Well, hydrogen peroxide can decompose into oxygen and water. And if you keep it too long, it goes off. So I get some more. So we got some more. There isn't very much of it, but perhaps this will be enough. I'm not very impressed, are you?
It's not the best thing I've seen.
Hydrogen peroxide has the formula H2O2, and it has quite a strange structure. This is a model that I use for the students. I'm sorry, the atoms are all the same colour, but you imagine this one and that one, the ones I'm holding with my hands, are hydrogens, and the two black ones are oxygen. And the important thing is you can see it has quite short hydrogen-oxygen bonds and a very long oxygen-oxygen bond, which is weak and breaks very easily, which is what makes hydrogen peroxide so reactive. It also has this rather strange structure that this bond is at right angles to that one. If I hold it up, this one is horizontal and that one is vertical. And so it has a rather strange symmetrical structure. I once hit myself very hard on the nose while demonstrating this in a lecture. So you have a long oxygen-oxygen bond that makes hydrogen peroxide very reactive. Pure hydrogen peroxide will set fire to almost all organic matter. So if you put it on a piece of cloth, whoosh, it goes up in flames. So normally people use hydrogen peroxide as a dilute solution. And here you can see we have one solution which is called 40 volume, which means 1 litre of liquid gives 40 litres of oxygen gas if it decomposes. And this sample here, which you can see has more aggressive warnings, a bit more dangerous, this is 100 volume. And so the hydrogen peroxide that you buy in the chemists for bleaching your hair is much weaker. It may only be 5 or 10 volumes. So this is 10 times stronger. You wouldn't bleach your hair with this. It might go up in smoke. Trying again, this time I hope a bit better. I put warm water in here so the reaction may be faster. and I'll put in most of the acid as well. Then a bit of permanganate. And now that we've got enough peroxide still left, you can see it's decolorizing straight away. That's pretty cool.
What's going on there, man?
So what's happened now, I didn't wash the thing out properly, and we had some peroxide left. And now it's reacting faster than we can add the permanganate. So this is actually much better than I intended, because I was going to make it purple and make it go clear. And here you can see I'm pouring in a purple solution, and it's disappearing.
That's brilliant.
And you can see it's releasing oxygen from the hydrogen peroxide. So when it hits the surface, the manganese, which is bound to oxygen in permanganate, reacts and loses its oxygen and forms manganese ions, manganese 2+ for those of you chemists, which are completely colorless. So it goes from this very intensely colored salt to the colorless one. So it's like magic, isn't it?
You have to remember this trick.
Yes.
Lovely. This wasn't what you wanted to show us.
No, but it's even better. I now have to explain to the technicians why I've used the whole bottle of permanganate solution. Thanks to the Nottingham Contemporary, I can show you a real experiment to demonstrate to you that you need air to make a candle burn. You can try it yourself afterwards, but make sure that I don't crack the sugar basin first. But you see, if you take the sugar basin, which is conveniently on your table, and if you put it over the candle then goes out. So you have in front of you there a ready-made experiment to show that without air, a candle won't burn. So, time for you to get a drink, and then you can ask some questions. Thank you. Perhaps I should describe what the first experiment that I did at school in chemistry, and which was to try and show the difference between a physical and a chemical mixture. And it was mixing iron filings, just small pieces of iron, with sulfur, which is yellow material. And so first of all, we were given some iron and sulfur, and we shook it up in a test tube. And so you imagine iron filings look all grey-black, and sulfur is yellow, so you've got a rather pale yellow greyish mixture. And then if you took a magnet, you could separate out the iron filings, which came out, made the magnet look like me with all the filings sticking out, and you were left with a yellow powder. So this was just a physical mixture. We were then told to mix them up again, and this time we put them over a Bunsen burner and heated them up. And the stuff went sort of jet black color, and this was a chemical compound of iron and sulfur. And so if you waved the magnet, you couldn't separate them. And then as a sort of bonus, we treated it with acid, in which the acid then reacts with it and makes a smell of bad eggs, so liberating hydrogen sulfide gas. So people got quite excited. There was a smell of a nasty smell, so they thought chemistry was involving smells. So the second part of the question is what holds atoms together? Well, atoms together to make compounds, yes. The things that essentially hold atoms together are electrical charges between them. Exactly how those electrical charges hold them together depends from one compound to another. So sodium chloride, table salt, you've only got sugar in front of you. But table salt consists of positively charged sodium ions, which are attracted to negatively charged chloride ions. And you can make it by burning sodium in chlorine gas. And if you're brave, once you've done the reaction, you can taste the salt. But I have a friend, David Jones, who's done this on television, but I would never do it. But so those are held together by electrical charges, and the atoms in a particular compound or molecule are held together with different strengths. So some compounds, the atoms are held together very strongly. In other compounds, the atoms are not held together at all strongly, and those are the sorts of compounds that tend to react very easily. You saw on the video hydrogen peroxide, where there are two oxygen atoms that are not held together very strongly at all. So in molecules, depending what the molecule is, the atoms can be held together more strongly or less strongly. Then, of course, the molecules can themselves form crystals. You've got some nice example. I'm sorry, you don't want sugar in your beer, so it'll be all right. So if you look here, you've got some really nice crystals of sugar, and sugar molecules have oxygen and hydrogen atoms on the outside of them, and the hydrogen molecules of one molecule interact with the oxygen molecules of the next, or oxygen atoms of the next molecule, which has a weak force that holds them together. So you have a large lump of sugar which will have hundreds of millions or millions of atoms in this, though the molecules, or millions of molecules in a piece even this size, but they're held together so you can have something of reasonable size. Did that answer your question? We will come back. You can ask about photosynthesis later if you want. So some more questions. I suppose I better eat the sugar since I've handled it now.
I have a question. I'm not sure if it's a question or more of
I'm not sure if your microphone is working.
I think it is.
Yeah.
Thinking about the way that you mentioned the way an artist approaches reactions and a scientist, and when you're working with experimentation and the video that you showed us, how much comes out of the accidental in terms of it being beneficial to the experiments that you're doing? Because obviously you have a very specific outcome that you're looking for when you're experimenting with different things, whereas with an artist, that uncontrollable or unpredictable outcome is what drives the experimentation. So I'm not sure if that really has formed a question, but it's more the nature of the different approaches between the two.
Well, I think that accidental happenings are very important in experiments. The difference comes with how, when you observe something, what happens next. And I mean, I haven't met Raphael Hefti, but he does something, says, wow, that's good, that will make a good exhibit. The scientist will say, gosh, that's interesting, I wonder why it's happening. The absolutely classic example, though it's not really, where it's on the borders of biology and chemistry, is Alexander Fleming, when he got contamination of one of his dishes in which he was growing bacteria with a mold, and he noticed that the mold was killing the bacteria, and from that he discovered the first antibiotic, penicillin. But the key thing is that his mind was already thinking, how can we kill bacteria? And he suddenly realized, gosh, the fungus is doing it. Let's find out how it's doing it. Rather than saying, that's a pretty dish, let's exhibit it. Now, I'm not saying that scientists are anyway better or worse than artists. It would be really boring if the world was just populated with scientists. And the thing is that to make objects that are aesthetically pleasing may require a completely different mind from those that require to be very analytical. You only have to look at some of the diagrams that scientists produce in their scientific articles to realize that they have zero sense of what is aesthetically pleasing. But there are some who are quite good artists as well. There's a question there.
Yeah, so is that really loud?
Yeah, no, it's fine.
It's actually a really similar question to the previous one, and I think it's going to have a similar problem in trying to formulate it into an actual question rather than just me speculating. But I'm a history student, so neither a scientist or an artist, sort of that uncomfortable middle ground that doesn't really have a methodology or a pretty result. And I was just wondering about similarities in the methodology between a scientist and an artist, because whilst an artist is neither trying to verify nor falsify a hypothesis, I thought there might be a similar relationship between experimentation and discovery, because historically there have been scientific discoveries that came about, like as you were talking about, by accident, and I guess I would speculate that the artistic process is about trying different things until you end up sort of by accident stumbling upon something that is aesthetically what you were aiming for and conveys the same kind of meaning. So is it not just like a very sort of a human constant between curiosity, between art and science?
Well, as you know, humans like to classify things, and we like to classify them into either A or B, whereas, in fact, many things are a whole spectrum and that there isn't necessarily a sharp boundary. If you think about artists, not so much now, but say in the Renaissance, they spent a lot of time essentially doing chemistry, trying to develop better pigments so that they could do their painting. And so, which is not very different from doing chemistry. What is very different is the attitude of alchemists. And I don't know a huge amount about alchemy, but they had this belief that a lot of things were known in the past, and we had to uncover the secrets again or learn from what the ancients already knew. Unfortunately, now with modern scientists, there is the completely opposite attitude. You know, what was discovered 15 years ago is boring and so on, and we're going to discover new and important things. And it is quite sobering to find out actually how well scientists did measurements in the 19th century. Some years ago, one of my students repeated an experiment that had been done in 1872, which the key thing was to measure a temperature at which something happened. And the student who measured it got a result that was 1/10 of a degree centigrade different from what was measured in 1872. So people then were doing very careful measurements, often better than now, because they weren't in a hurry to publish things and show that they were better than their foreign rivals. But I think that, if you like, I've been set up by Emma to find a real difference between art and science. And I mean, in my own family, my brother is a playwright. You can buy his DVDs on Amazon if you haven't seen his films. And so I'm used to the difference between art and science. I should say that he once wrote a play about a chemistry department, and I had to produce a few lines of dialogue about chemistry. It's the only time in my life that lines written by me have been performed in the National Theatre. And on the opening night, I sat there, and I was the only person in the entire audience who laughed when one of the actors said hexafluoroisopropanol. And I thought this was very funny and laughed, and nobody else did. But I think we sometimes exaggerate the difference. But it is also important to realize that even within science, even within chemistry, there are people who are trained in different ways, either because they have had different supervisors who've trained them, or perhaps because they've come from different countries. And when those people look at the same problem, which is identical, the atoms, everything is the same, they can see and analyze it in a different way. And this is why quite often, if you have a multidisciplinary team of scientists, you can solve things much better than just one particular or a whole group of people who think the same way. There's another question, Chloe.
Hello, I'm an artist, but
Yeah.
I've got a problem, really. I'm a visual artist, but now I'm wanting to go into using smells,
Yeah.
because they're quite nostalgic, and you can place them and they boo up on you, you don't know they're there. But then I've just finished education, woohoo, and thinking I will have to go back into to do chemistry in order to go in the direction I want to, which is like, I don't think I'm ready for that yet. What would you suggest, sort of, and where to start? Because obviously I've been mixing up smells, but I don't know anything about what's actually going on. It's all invisible to me.
Well, I should say that chemists, by and large, have a very bad sense of smell because they work in buildings where chemicals have been used. The building I work in, the chemicals have been used there for 50 years or something. And so a few years ago, a tree surgeon, who saws trees and spends all his time out of doors, came into the chemistry building. And even in the foyer, where there are no chemicals, he complained there was a terrible smell, and how could we possibly work there? My answer to you is that it'd be brilliant if you want to do art based on smells. But the first question you have to ask yourself is how good you are at smelling. And I don't know if you realize that perfume companies have special people who work for them who are known collectively as noses. And they sit in special offices with rows of bottles of different smells, and then somebody comes along and says, I want a perfume made up that will suggest space flight or Doctor Who or whatever it is, and these people mix away and make them. And these people have fantastically developed sense of smell. And I've been told that they're really fussy, and if you give them a new chair for their office, they will begin with the chair outside the door, and over a period of days, they will gradually bring it into the office so they can get used to the smell. And the person who was telling me this, who works for a perfume company, is not a nose, said that he went with one of these noses to Malaysia. And in the hotel, there was a big swimming pool indoors. And so they went into the swimming pool, or into the room where the swimming pool was. And the guy telling me said that all he could smell was chlorine from the swimming pool. And the nose said, Chanel number 5. And so the chap who was telling me looked round, and the far end of the swimming pool, there was a woman on a lounger. So he walked around the swimming pool up to this woman and said, are you using Chanel number 5? And the woman said, yes, how do you know? And it was this chap at the other end. So if you're going to do art based on smell, you've got to be very good at smelling. And so what you probably ought to do is to approach a perfume company and ask if you can visit, and they'll give you a smell test.
Thank you.
Have we any other questions from the audience? Anybody?
Hiya. Sort of the question that I was wanting to ask was sort of a more kind of question about your general history in science, because obviously curiosity is really important when you're trying to understand and learn new things, but has there ever been anything that's kind of never stopped filling you with wonder, sort of something that's never stopped surprising you?
Well,
What was the speaker's origin? I mean, where's he coming from?
yes,
I'm a chemistry student.
you're a chemistry student. Well, what I should say is that doing scientific research is very like an addiction. You get really excited when something new is discovered. And some of my most exciting moments have been turned out to be complete rubbish. I mean, one of the first ones I can remember was during my doctorate. I had a frozen solution. I was working by myself late at night in the lab, which one shouldn't do. And I had a frozen solution which was shining a very bright light on it. And so it was a solution, so it was a liquid that had a chemical dissolved in it. And I switched off the light, and you can imagine it was rather dark in the lab, and this frozen solution started glowing bright blue. And I was really excited because the compound, the chemical that I dissolved in it, was not meant to glow at all. So I went home, and I could hardly sleep all night. I'd made a fantastic discovery. The next morning, I thought I'd better check. So I just froze the liquid without the dissolved chemical, and it glowed just the same. So it was rubbish. But I'd had this huge sort of rush of discovering something. And so I think when you're trying to discover new things, it's almost like, you get I'm not sure whether it's an adrenaline rush or whatever, but you get excited. And once you've discovered it and you've written the paper and so on, you don't forget about it, but the next thing is the most exciting. I was quite lucky at school because I did one of my exams a year ahead of all my classmates. And it was a so-called S-level exam. It was sort of an extra bit of A-level. And so that I was still at the school, and for a whole year, the chemistry class was working to take an exam that I'd already taken. So I was just told by the chemistry teacher, you just work over there and don't interfere with the lessons. So I had a whole year playing around with chemicals, which in retrospect was completely wasted, but I really enjoyed discovering things. I mean, there were some dreadful moments. The school had what in those days was a very expensive piece of equipment for measuring how acidity, a so-called pH meter, and I broke it. And it cost £5, which in those days was a lot of money. Just to give you a sort of calibrate that, my wife and I, the hotel that we spent our wedding night in cost £8 for a sort of bed and breakfast, and so here so it was very expensive. And I was really terrified what the school would say. But the excitement of doing experiments is something that you can really enjoy. But the other thing is that experiments like the one I showed you on the video, I can still get quite excited about. I mean, the colors of these chemicals are something that still give me great pleasure. And even though you know the explanation, seeing the purple color disappear still seems a bit like magic. So more questions. Does that answer your question?
Hi, Professor. I guess my question is more to deal with the flip side of things. Science, especially research, is very sort of results-driven. Having just come out of organic chemistry labs, where everything has failed, how in your life have you had to deal with failure, especially in science itself, given that with all the pressures you've got and you're always aiming to make something? How do you deal with when it doesn't work?
Well, there are two things. Just to say to you that I failed my organic chemistry at university, so I sympathise with you. But I think often you can learn a lot from experiments that don't work. The problem is nowadays that there is increasing pressure on people to publish. And you can't publish papers saying, I tried this experiment and it didn't work, even though that could be really important. And for people who are doing doctorates, it's very important, and I encourage them when they're writing their PhD thesis, they can actually describe the things that don't work. And that's important, first of all, because it may give people ideas in the future. It also stops some poor chap repeating the experiment later on and finding it doesn't work either. But I did very badly in my final exams at the university. I was really upset, as you can imagine, but in retrospect, it was one of the best things that happened to me. And I think everybody has to learn to deal with failure. The advantage, if you're a chemist, that there are almost an infinite number of chemicals, and if this doesn't react, there's another one. It's not nearly the same as being a writer, and you write a book and put your whole life in this book, and then it's a complete flop. So I think chemists actually have things quite easy compared to, look at the poor artist who's about to start out on her career, has got a lot more at stake than somebody trying to do a chemical reaction. So.
Hi, Martyn.
Hi.
I just find the use of colours in chemistry and the use of colours in art, I mean, I've dabbled a bit in art, but and I work in the chemistry department, so I find the use of colours very, very interesting, and the importance of colours. Sorry.
Yeah. Well, I don't know that perhaps you're not aware that a huge number of the chemicals that you can, there are lists of all the known chemicals, which I can't remember. It's now got well past 50 million, but some quite sizable chunk of several millions of those are dye molecules. And this year, as you know, we're celebrating, or marking, celebrating is perhaps the wrong word, marking the centenary of the start of the First World War. When the First World War started, the khaki dye that was used for British Army uniforms was made in Germany. And somewhat understandably, the supply dried up fairly quickly. So they were reduced. The British Army was reduced to dyeing the clothes with potassium permanganate, the purple stuff you saw in the video, which if you put it onto white cloth makes it go brown colour. It doesn't last very long, about 3 weeks, but given the rate at which people sadly were being killed, that was sufficient at least to begin with. And so the dye industry is absolutely fascinating. The first dye, or artificial dye, was discovered by a chemist called William Perkin when he was 18. He was trying to do a chemical reaction which didn't work. He was trying to make quinine, which was then used for treatment for malaria, and instead he got a rather nice purple colour, which he realized could be used as a dye. And so he and his father set up a company to manufacture this dye, which he called mauvine, and from which we get the colour mauve. So they invented, I think, the word mauve. And in Victorian times, until this had been discovered, purple clothes were fantastically expensive, and then this dye was discovered, and everything was made. Everybody was going around with purple umbrellas, everything purple, and or rather mauve rather than purple. And so it's very good to you who are chemistry students. Perkin set up a company with his father to make these dyes and was a millionaire by the time he was 30. So he then retired and did chemical research for the rest of his life. And his son became a chemistry professor and had a big beard. So you ought to be a good organic chemist with a beard, because one of the problems when you're doing chemistry is if you have a solution, you want nice crystals to form of your product. And to form good crystals, you need a tiny speck of dirt or something for the crystal to form down, to nucleate. And all sorts of gunge fell off Perkins' beard into the thing. And so don't comb your beard too much and your organic chemistry will go much better. But I think nowadays, dye color can be extremely diagnostic of what is happening in chemical processes. And one of the things that I think is fascinating, coming back to photosynthesis, which was mentioned. Photosynthesis, as you know, is the chemical reaction whereby sunlight is absorbed by the leaves of plants, by the green pigment in plants, chlorophyll, and carbon dioxide is absorbed and oxygen is emitted. This is what makes our planet livable on. And I've always been fascinated how in the autumn these color of the pigments in the leaves change. So they go from green to the bright colors. And it's particularly striking in a tree called copper beech, which has deep red leaves, which then in the autumn actually turn green before they go orange and display. So that they're fascinating chemical reactions which you can relate the color to what is happening in the molecules. It's in the leaves. It's almost art. You know, you can stick leaves on things and make pictures. Perhaps you should become an artist with leaves. It's much easier than with smells. So more questions. Yeah. Yeah.
Thank you again. Would you speak on ACT synthesis and relate that to the possibility of establishing a complete distinction between physical reactions, biological and chemical reactions?
No. What do you mean by ACT? I'm sorry.
Sorry. ACT synthesis?
Yes.
Would you explain that
I
one?
don't know what ACT...
I'm trying to remember the correct terminology here, but the means by which energy is provided for cells.
Oh,
ATP, excuse me. There you go.
ATP.
Yeah.
Well, let us begin slightly differently. If you take a Mars bar, which contains about this much sugar, perhaps slightly less, but I haven't weighed this. But, and if you take that amount of sugar and react it with oxygen in a chemically efficient way, for example, with liquid oxygen, it will produce a vast ball of flame. Whereas if you eat a Mars bar, flames don't come out of your mouth. So, but your body converts the energy of a Mars bar into the energy you need to do things. And it does this through a molecule that is called ATP, adenosine triphosphate. And this molecule loses one of its so-called phosphate groups and gives out energy. And then in your body, there is an enzyme, a catalyst, that puts the molecule, regenerates the ATP. Now, it is quite a sobering fact that each of us, if we don't do too energetic work in a day, our body generates about our whole body's weight of ATP. So we have a bit of ATP, and it keeps on regenerating. So if you calculate how much it is made in a day, it is a huge amount, approximately equal to your body weight. And so in my case, 75 kilos or whatever of ATP, which is quite a sizable sack. And the way that it does it is really quite an extraordinary piece of chemistry. I should say that most of the chemistry that goes on inside our bodies is really quite complicated. Sorry. There are a few fairly simple reactions, like one of the first steps of digestion is reacting things with hydrochloric acid. I'm ashamed to say our most successful video shows what happens if you put a cheeseburger into hydrochloric acid. And this has been watched by 8.6 million people. In the United States, health clubs are now showing this video to people to say, this is why you shouldn't eat junk food. But most of the chemical reactions in the human body are really quite complicated. And in the case of ATP being synthesized in your body, there are molecules that behave rather like a miniature stapler, in the sense that you have the two bits of the ADP, the one that the starting material, and phosphate, and in this so-called ATP synthase, these two bits are brought together and, as it were, stapled together. It's not really stapling because there is nothing holding them together, but they're pushed together. So there's a little machine, as it were, working, or many, many of these nano machines inside you. And it is really, in some ways, an extraordinary, almost sort of miracle, how in the human, or any organism, even bacteria, let alone all our cells, how the chemistry, which is so complicated that chemists would never dream of trying to build the chemical process on these lines, how these things work so efficiently. If you think about it, most people have bodies that work quite efficiently for 80 years or so, and with only minor repairs, hopefully. And there are not many machines that we build that will last that long. You know, you get quite excited if your phone goes for 3 years without giving out or whatever. And your car will probably give out long before that. So of course, humans have the advantage of billions of years of evolution, which has honed these reactions, and presumably there were less efficient reactions which were evolutionary sign lines that didn't make it to the present day. More questions?
Thank you. I have to apologise again for another speculative question. It's what we're prone to do in the humanities, speculate wildly. Some would even say pointlessly about things we know nothing about. So I live with a lot of scientists, and the exhibit in question is about visual snapshots of experimental scientific processes, which have been represented like aesthetically, artistically. But I always notice, and I'm sure it causes them a lot of pain, but I don't study it, so it's fine. Like the theoretical, diagrammatic representations of like chemical theory are quite aesthetically pleasing. They have like an inherent aesthetic value, and I think people have noted for years that people who don't study maths would think that a sheet of mathematical equations is interesting to look at, even though it is meaningless to someone that doesn't know what the numbers mean. So I guess the question I'm trying to ask is do you think that there's any value either to science or society for a relationship between science and art?
Oh, I'm sure there is. There's a great value. There are various different levels. First of all, even scientists have some aesthetic sense and saying this looks nice, that doesn't look nice, and making your theory or your representation of something looking more aesthetically pleasing is great for everybody. But I think the other thing is that it is extremely helpful in science for those who are not scientists to ask really simple questions. Rather like not quite the level of the emperor's new clothes, but asking questions which chemists will not necessarily ask. I mean, when I teach students, in some ways it is much more fun teaching the first-year students than the students who are near the end of their course. Naturally, the students who are near the end of their course know a lot more and can ask more challenging technical questions. But it is the students at the start of their course who have not been brainwashed into thinking like us, who ask questions of the type, like your friend over there, like, what is an element? Which really make one stop and think. By the way, my wife says I haven't answered your question yet, so I will try and answer it in a minute. But I think it never hurts to be asked naive questions. And you as a historian should never be shy of asking your science friends questions, because it will make them think. But you have to be prepared for them to ask questions about history that you might not have thought of. So Chloe, our artist, our perfumery artist, has
I'm just
a question.
thinking, am I the only artist here? I'm in a gallery. I was just going to say, we were saying earlier about you're not allowed to publish something if you've got it wrong, because that's put it away.
No. What I was saying is, I should have perhaps explained that if you write a scientific paper, I and my colleagues have finished a paper today, about an hour before I set out through the traffic jams to come here. And what happens is that is sent to a journal, scientific journal, and the editor of the journal will then send it to some other scientists, chemists, anonymously to me. And they will read it and decide whether they believe the results, and also to comment and see if we've made mistakes and so on. Now, nobody would ever want to publish something that was deliberately wrong. And there are examples of fraud in science, but they are remarkably infrequent. Because the thing is, if you're found out to be cheating, it's like being found out cheating in a casino. You're never let in again. And so your reputation for honesty is probably the most valuable asset that any scientist has. Now, that doesn't mean that you can't be wrong, but what you have to say is that I've done these experiments, here are the facts as I have observed them, So I think this is happening. And somebody else may do some more experiments, find some extra facts, and show that your explanation is completely wrong. But that's okay, provided that at the time it seemed a sensible explanation. What I was saying is that if you try an experiment which you're hoping is going to work, I've got this chemical and that one, I want them to react. And even though I bring them together in every conceivable way that I can think of, they don't react, then there's really nothing to report except I've tried lots of things and it doesn't work, like our bearded chemist over there. And the thing is that, so that's something which you can't easily publish, even though that could be the absolutely key missing piece in somebody's theory, that if they only knew that those two things didn't react, their theory would be perfect or whatever. But on the other hand, I don't know that that person exists, so I can't publish that.
Okay, thanks for that. I was just going to say, I think with the importance of art, the relationships between art and science, and then artists and scientists, what we can learn from each other. Yeah. The sort of dynamics of now you've off you go into the world. If I was to put on an exhibition and it didn't go down well, it was probably because it was the difference between subjective and objective. I'm making up my own facts. I'm doing things through my own head, and if people don't like it, then that's up to them, rather than it's not right. So maybe I can take something from scientists and say it has to be right. It has to work because there is a scientific basis behind it. So thank you.
Yes, I would say that you can, if you're a really principled artist, display your thing, and then people say it's not nice, and you can say, well, you don't understand it. But on the other hand, you have to be pragmatic, you have to live. So you want people to say it's nice and buy it, or say this is outrageous, but I will buy it because I want to shock my friends or whatever. So you want to get a reaction from them that will loosen their purse strings and make you into Damien Hirst or whatever. So that, and in the end, scientists also have to, I suppose every scientist needs to feel that somewhere in the world there's at least one other scientist who is going to be interested by the results of this experiment. It may be that there won't be very many because it's very specialized. In some areas of maths, there may only be half a dozen people in the world who can understand what a particular mathematician has done, but they have to feel that there are some of these people out there.
Thank you. What you were referring to appears to be the notion of a repeatable, falsifiable hypothesis, on which Karl Popper wrote famously. So for anybody who hasn't heard of that phrase before, then that's what was being referred to. Yeah. But also within science, there is observation, very often that cannot be backed up with experimentation. A lot of physics, I would argue, and astrophysics is not amenable to experimentation. We can't remove ourselves from the environment which we're trying to conduct experiments on. So perhaps the public, some people in the public may have heard of repeatable, falsifiable experimentation, but perhaps they're not aware also that large areas of science, physics and astronomy principally, are not amenable to experimentation. And this is not really made very, very public by those areas. Thank you.
So, I mean, I agree. I mean, it's fairly obvious that you can't go with your test tube to a star and try chemical reactions on to see what stars are made of. Though there is a very exciting thing, as you know, next Wednesday there is the lander that, all being well, is going to land on a comet, which is something, when I was your age, one could have not even dreamt of. But I think what would happen, I'm not an astrophysicist or whatever, but usually what astrophysicists will do, they will observe something and think of an explanation and then say, if my explanation is correct, because there are so many stars, I ought to be able to see the effect that I'm predicting from this explanation. But I would say that conjurers believe that scientists are the easiest people to fool. Because you see, scientists are trained to believe what they see. So if you can cheat them, sort of hide something or whatever, they just see it's gone and they don't notice because I point over and say, look at that light, and do something, you see. And they don't, and they believe things in a way that that more ordinary members of the public say, God, that must be cheating. And I've had one example in my career where we did some experiments, and in fact it was measuring the amount of gas in different samples. And it turned out that the amount of gas depended how that sample had been treated before it came to our lab. So although there were a whole series of things that looked identical, some had been lying down, some had been in the sun, and so on. And it felt really strange because we were repeating what should have been identical measurements and getting different answers. And so I suppose everybody doing science feels that nature is not going to cheat. And therefore you feel slightly uncomfortable when you find, when you do the same thing, different things happen. I should just say, you mentioned artists and scientists. You perhaps don't realize that the word artist is quite an old word, ancient word, but scientist was only invented in the 19th century. I think in the 1830s at the meeting of the British Association, somebody got up and said, I think we ought to have a word to describe those who do science, like artist. What about scientist? And people thought it was a really ugly word for a long time, and there was quite a lot of argument whether you should talk about scientists or not. But now we forget that completely. The word chemistry is quite old. I think it was first used in English in 1605. So in 2005, I wrote to the Royal Society of Chemistry and said, chemistry is 400 years old, we should celebrate. But they were unimaginative and didn't do anything. So, any more questions? Yeah.
Yeah, I feel quite bad asking another question, so if anyone else has anything to say, please do put your hand up before I have a chance to. But as we were just talking about the skepticism of the untrained public who haven't got a scientific education, who may be quite critical in an uncritical way, and then sort of the open-mindedness that maybe scientific research requires, seeing as we're talking about like the links between art and science, like when you watch an old science fiction show from, say, the 1970s, we talk about we have to suspend disbelief for it to have any aesthetic value. So for the sort of the outdated special effects that we're not used to give an impression to you as the viewer, you have to suspend your disbelief that it's obviously made up. So like when you were talking before, I was just trying to clarify really, are you sort of saying that maybe sometimes scientific discovery or the process requires you to sort of suspend disbelief or the things that you would be expected to disbelieve in order to like remain open-minded enough to understand the way that nature actually works, especially if it's not what you were expecting?
No, what I was saying is that, I wasn't saying quite that, but that scientists are trained to observe things in a quite a specific way. And if whatever they're observing is cheating, they might not observe, they might not notice it. So that I would have thought in some scientific subjects like psychology experiments, if the subjects are deliberately set out to mislead the scientists, they might have quite a good chance of doing it if they're aware what the experiment is and so on. Whereas, fortunately for me, and the molecules don't really have any opportunity of cheating in that way. Though there have been some papers which I've only read reports about them, that mice and other experimental animals behave differently if they're looked after by men or women. Possibly because men and women smell differently to the mice, you see. So you may not be controlling the conditions, or it may be that, and I won't say which sex, one sex may be more loving to the mice than the other, and this will make them behave differently. So it is quite difficult, especially in biological experiments where biological organisms are complicated, to make sure that you're controlling all the conditions completely. In fact, in quite a lot of biological research, one group often has difficulty in repeating the research that has been reported by another research group. By and large, in chemistry, things are much easier to reproduce, provided that people describe all the things they've done in their experiments. But really, one should only believe the results of an experiment if somebody else can do some completely different team can repeat the experiment under different circumstances and gets the same results. This brings me quite nicely to the elements, and I will define them in a minute, but there are some elements on the periodic table right at the end. They're not on this periodic table. There's some which have to be actually synthesized, made. And you need very specialized high accelerators that cost many millions, if not billions of pounds. And after one team has claimed to have discovered a new element, the result is not accepted until a completely independent team has managed to repeat those experiments. Because the original discoverers really want the results to be correct, and they may be fooling themselves. Or somebody might be cheating. There is a case of element 118 where the original discovery was somebody cheated and made up their results. But I'm sorry, I've forgotten what your question was. Have I answered it? Okay. So I should now try and come back to your definition of elements. And I think the way perhaps to explain this is that at the level that chemists understand, as opposed to particle physics, all atoms are made up of three different sorts of particles. Electrons, which have negative charge, which is what conducts involved in electricity, protons that have positive charge, and neutrons that have no charge. And if for a moment you forget about the neutrons, and just have the positive and the negative ones, you can see that you can make up different, and all atoms are electrically neutral. They have similar number of positive and negative charges. So you can begin with having one electron and one proton, or you can have two electrons and two protons and so on. And each of these atoms, which has a distinctive number of protons and electrons, will be chemically distinct and is what we mean by an element. Some of the arrangements of protons are unstable, so the elements are short-lived and fall to bits. Others are extremely stable, like hydrogen, which have existed more or less since the time of the Big Bang, or a few billionths of a second after the Big Bang. And so what Mendeleev did, knowing nothing about protons and electrons, in fact, I don't think he even believed in electrons when they were first discovered, he saw an arrangement of elements based on their chemical properties, which in fact reflected the number of protons and electrons that they have. Though he just arranged it like a random set of letters, rather like on the keyboard that you can see over there. And the idea of the element and that different sorts of atoms were, or different types of atoms were chemically distinct, came long before anybody knew about electrons and protons. Now, particle physicists see that protons, neutrons are made up of so-called quarks, which I never really understand. But from the point of view of chemists, you don't need to worry about that. Is that a slightly better answer?
I think perhaps...
Each element, when you dig it up or whatever from the ground, or you find it, has a so-called characteristic weight, which you assume for convenience, or originally they assumed that hydrogen had a weight of 1, and so they were then in multiples of the weight of hydrogen. The definition has changed slightly, and so for every element, and I don't know whether it's here on the periodic table here, though I can't read it, they have the so-called atomic weight of the element. One of the hardest videos that I've ever had to make was when there was a minor adjustment of the atomic weight of a few elements. Because some elements, like lead, are have been formed on the Earth partly by decay of radioactive elements. So the lead that is dug up in one part of the world may not have exactly the same atomic weight as another part of the world. And so it was decided that from the point of view of tables, that lead could be allowed to have an atomic weight that was in a small range of allowable weights. And so we decided to make a video about this. And I had to shoot the video 3 times because I was told, you're not being enough enthusiastic about it. And even after the 3rd time, when I'd really wound myself up a bit, I still thought it was an exceptionally boring topic. And then a week later, I was in South Africa, and a woman came to my lecture with her teenage son and came up afterwards and said, fascinating video you made about atomic weights. And I realized that in the world, all over the place, there are people who are really and geekishly interested in the most obscure aspects of chemistry. But it's good. We can keep them intellectually satisfied. But it is not those people who are going to make the real breakthroughs in chemical science. So you can be a chemistry student without getting desperately excited about atomic weights. Though perhaps you do, Alice. So I don't know if there are any more questions. I think people are getting tired.
I think maybe if we... one more short question, and then maybe we'll wrap up for the evening.
You've spoken much more about science than you have about artworks, I think.
Yeah, I think that's
and I
quite...
wondered what your motivation is for this evening.
Motivation this evening? Well, I mean, the immediate motivation was that Emma invited me to come and speak, and therefore, so the point is that I can't talk about art in a sense, because I have I have personal views on art. I like some things, I don't like other things, but that is personal prejudice, and I can't speak from a technical point of view. And even if I could, I'd probably be boring. I might be boring about science. But on the other hand, I do think that the distinction between art and science is sometimes made much more greater than it is. And some very famous scientists like Humphrey Davy were very closely associated with some of the leading poets of the day, like Coleridge, and they wrote poetry. I've never been able to write a word of poetry, and I was cured of poetry by having to translate The Charge of the Light Brigade, into the Valley of Death, etc., having to translate that into Latin as part of my school exercise, which is one of the most pointless things I can remember from school, though perhaps it was character forming. But so I don't think that I can say anything very useful about art, except to react with things like Raphael Hefti's displays from the point of view as a scientist, saying what I think is interesting and what is not interesting. And also, I suppose, you can take it to a higher level and thinking, why did he, as an artist, think this, which I think is a bit boring, was interesting? And so, but he would probably be equally intrigued by what things I liked and what didn't. I was hoping he would be here and we could have a dialogue or a battle. But unfortunately, it's a one-sided victory because he resigned before the battle started.
Well, I think maybe on that note, we'll finish for this evening, but just to say a very big thank you to Martyn for a very interesting presentation discussion. Thank all of you for your questions as well, and I hope that it has ignited some interest perhaps in the visual arts.
Interesting.
And certainly I think my chemistry teacher, who was so disappointed with me, would be delighted that I'm revisiting chemistry. So and those of you who haven't watched the videos on YouTube, I would urge you all to take a look. They're absolutely brilliant. So yes, thank you all again.